Okay, so during the next part of, and the sort of this is, I'm not going to have time to discuss John Porco's work. So what I'm going to do is I'm just going to finish up the work on one of my favorite biomimetic cascades, which is the Endiandric acid cascades. And this is some of the work done by Casey Nicolau. Okay, so so in general, the Endiandric acid cascades involve what are pretty, I think it's some of the most remarkable rapid complexity building molecules. Hopefully it'll become clear once I'm done drawing them how impressive the sort of structure behind these are. Hopefully I don't screw up drawing them. Okay, so this is a molecule, there's a whole class of these molecules. Okay, this is called Endiandric acid B. Okay, so again, you've got this sort of 6-6 ring structure, 5-member ring here, 4-member ring here. It's very compact bicyclic structure. And I'll show you another one that's also a member of the Endiandric acid, another member of the Endiandric acids that is slightly different structurally. Okay, and this is going to be Endiandric acid C. And so there's a whole class of these, but I think for the point of sort of explaining the points that I want to make here, we're going to focus just on these two molecules specifically. Recognize that there are more molecules within this class, but the point of today's talk will sort of, I think hopefully, or this part of today's talk will hopefully illustrate how quickly and efficiently molecules can sometimes be built up. So again, steroids is a perfect example, right? You generate this sort of polyene compound, you treat it with a little bit of acid, generate this carbocation, set off this carbocation cascade, where you generate tons of different molecules, or tons of different bonds at the same time, all the stereochemistry, and everything else. Endiandric acids are, so this is endiandric acid C. Okay, and what we're going to see is that both these molecules, in addition to the whole class in general, we'll see is that these can all come from, again, a much simpler sort of starting point. And that is going to be, at least the hypothesis was, that these are all going to come from they're both going to come from this molecule here. Okay, so the level of sort of complexity that's going to sort of set off this is going to sort of, I think it's kind of quite remarkable how something that might look as simple as this might actually be the precursor to what, at least on the surface, look like very different molecules. And so Jing already has a look on her face like, you already appreciate how, yeah. So anyway, so this is going to be the starting point, and what Casey Nicolau, and we're going to talk about his synthesis, what he does, and what the sort of point of a lot of the work behind his is that can he sort of prove that similar starting materials can be the basis for this class of natural products on the one hand, and on the second hand, can you try to replicate this process in a lab and try to sort of harness this level of complexity building, right? So I think anytime I start talking about this, the other thing that I really like about this process, I think it gives us a really good way to sort of go back and revisit Woodward-Hoffmann rules, because oftentimes we don't think about Woodward-Hoffmann rules too much. We sort of get lazy and we might not think about orbital overlap and sort of stereochemistry that can come from orbital overlap. So I think it's always good to sort of remind ourselves of this and try to at least put that in the part of the brain where even if we're not working on it, at least we can sort of recall it and go back. And anytime I start thinking about sort of the rules of molecular orbital theory and sort of how different things will react with one another, I always sort of go back to the staple, or the first one that we've ever learned, right? And that's going to be the Diels-Alder reaction. So I always just like to start thinking about the Diels-Alder reaction in general, right? And so if you think about Diels-Alder reaction, right? The reason why Diels-Alder reactions take place thermally, right, is that what you have is you have to start thinking about the sort of molecular orbitals, right? And in this system we have sort of right these sort of molecular orbitals that you start thinking about the nodes behind them. And again, when we sort of draw these out, depending upon, again, this is sort of mathematical and sort of what we're discussing here is more physical organic, but at least from the standpoint of thinking about stuff and rationalizing stuff, we're going to think about the relative interactions between sort of HOMO of one system and LUMO of the other. And so what we do is we sort of look at these different energy levels. This will be a refresher to you guys that will hopefully make the transition to Witten-Hawken rules make a little bit more sense, right? But, oh my God, don't tell me this marker's going to die. That's great, right? So at the lowest energy, we're going to have sort of no nodes, right? So there's going to be, in terms of a sigmoid, it's just going to be like, right, no nodes. The sort of second highest energy is going to be sort of one node, right? So we're going to have something that might look like this, right? The other one, we're going to have two nodes, depending upon where they are and where you want to put them. Sort of shift it, but again, the point is that there's going to be two nodes here. We have a node here and a node here. And the last one, we're going to have three nodes, right? And sort of the idea behind this whole sort of system is that, you know, the electrons, as we sort of go back and start filling these electrons, right? We have sort of 4 electrons in the system, and then again, as we go up and start filling these up, we recognize that this is the highest occupied molecular orbital, right? So this is our HOMO. This over here is our LUMO, right? And then again, on the alkene, we've only got no nodes and one node, right? And so in this case, again, we have 2 electrons, and so this is our HOMO, and this is our LUMO. And again, just sort of rationalizing it, even, you know, I don't really understand the math at all, but at least in terms of rationalizing it, right, it's fairly simple to just sort of think about the fact that when one bond is going to form with another bond, right, the highest energy of one electron, right, is going to, and the highest electrons from one orbital is probably going to react with the lowest electrons from another orbital, right? Those are going to be the most likely, the highest energy at one state versus the lowest empty one at the other state, right? And so, again, depending on how you're going to do this, we can start thinking about inverse electron demand or normal electron demand. Doesn't really, you know, the point is that the LUMO of one case is always going to react with the HOMO of the other, and vice versa, right? So, and the way that we know this, right, is that when we sort of look at how these nodes are going to line up, right, we sort of look at the sort of nodes, and this is sort of symmetric at the top at the ends, right? So if we would draw this, if we were to imagine this to be the LUMO, and this were to be the HOMO, we sort of have this symmetric orbital overlap, right? And then likewise, if we want this to be the HOMO, we want this to be the HOMO and this to be the LUMO. Right, now we have, again, the sort of nodes are lining up again. So this is sort of the way that we at least rationalize, and I think Diels-Alder is always a good one to sort of think about. This also helps us to the same extent rationalize, at least in part, it helps us sort of rationalize photochemical processes, right? Because if instead, if you had a LUMO and a HOMO, if we just sort of think about the standard alkene-alkene process, right? We know that thermally this isn't going to happen, right? So right, because now what you have is the HOMO of one trying to interact with the LUMO of the other, and now we don't have that orbital overlap, right? So one of them matches, and the other one is a mismatch, right? And so thermally, 2 plus 2s don't happen. Again, you guys should all know this very well at this point. But on the flip side, right, it can also be used to sort of explain the photochemical process, again, because what happens in a photochemical process is you're going to excite the electrons, right? And so what's going to happen is you're going to get one of these excited, right? And so now this becomes the HOMO, right? And so now what you're going to get is the HOMO of one molecule interacting with the LUMO of another. And again, if you sort of are confused about this, it's not, again, when you start thinking about photochemical stuff, sometimes you'll think, well, where's the LUMO here? It doesn't work that way, right? It's you're not exciting all of them at the same time. So the excited form of one is then going to react with the non-excited form of the other. But the point is that now you have the HOMO of one interacting with the LUMO of the other, right? And that's going to allow us to sort of get this reaction down. So again, I think as we start to get into Woodward-Hoffman rules, it's sort of good to, I think, refresh on some of the sort of basics of molecular orbital theory with respect to sort of electrocyclic processes that involve sort of extended pi systems, right? And so from the standpoint of Woodward-Hoffman rules, if we take this to the sort of next level, and we start to think about electrocyclic processes, the same sort of ideas can hold true, right? So again, an electrocyclic reaction, this is sort of a 6 pi electrocyclic ring closure, right, where you would go right, so it's kind of like a cope, but with an extra pi system in there. So this is what we would call a 6 pi electrocyclic ring closure. Okay, but the fact of the matter is that the important point here, as it's going to relate to the Endiandric acid cascades, and this is going to relate to sort of molecular orbital theory, and why we need to know it, is that there's a specific so if we go, let's just So again, when this electrocyclic ring closure takes place, right, we can imagine one of two different things forming. Okay, so we could have, again, when you have something here, now you're bringing on stereochemistry. And so you can imagine that when this happens, one of two different things can take place. You can either get the cis form, or you can get the anti-form. Okay? And so in this process, like, or again, depending upon what the stereochemistry is over here, you can imagine getting slightly different things. But the point that I'm trying to make here, hopefully, is that, and what I want to make is that there is a right answer here, and that right answer is going to be dependent upon sort of molecular orbital theory. And so instead of just going ahead and telling you what it's going to lead to, we'll sort of discuss this in terms of molecular orbital theory, and we'll sort of think about this, okay? And so from a molecular orbital theory standpoint, what we want to think about is the fact that this is a 6 pi electrocyclic process, right? Hopefully I have enough board space to do this. I might need to go in rows of 3. Okay, maybe that's all I'll do. 2, 3, 4, 5, 6. Okay, you know what? I'm just going to go straight into HOMO. Okay, so and down here we'll just say, right, so we've got 6 different potential molecular orbital sort of depictions that we could have here again. And so, you know, as you would imagine, there's 6 electrons in here. And so as we sort of fill up, there's going to be 2. There's going to be sort of 3 that are going to be filled, and there's going to be 3 that are unfilled. And so instead of, again, this is going to take me forever, and I'm nervous about this running out of ink and running out of time. But if just ignore having to fill out everything like we did for the Diels-Alder, how many nodes are going to be in the lowest one? 0. So let's just think about that. We'll just put out the outside one. So if there's 0, then everything's going to be on the same side, right? So we can just sort of fill up this one. Right? And then the second one, how many nodes are going to be? 1, right? And so now there's going to be some sort of break in between, and it's going to be opposite, right? And then the next one, right, there's going to be 2 nodes, right? And so at the point of 2 nodes, it's just going to go sort of back and forth, right? So again, even regardless of where we're going to put this, it doesn't really matter. There's going to be 2 nodes in there. We can just pick 2 symmetrically here, and we can just say that our sort of molecular orbital diagram, sorry, sort of our MOs are going to look something like this. And then again, at the LUMO, again, it doesn't really matter where we put these in here, but there's going to be 3 nodes. Right, but the important point is now we're sort of at opposite ends with one another. Okay, so if chemistry, so in the Diels-Alder reaction, we had sort of the HOMO of one interacting with the LUMO of another. If you were to assume in an electrocyclic process, we're not dealing with a HOMO of one versus a LUMO of another, right? We're dealing with an electrocyclic ring closure. So if you were to just guess just intuitively, which of these is going to represent the molecular orbital where the chemistry is taking place, where would you think it would be? So I've got 1 vote for HOMO, got 1 vote for LUMO, HOMO, Kishore, HOMO or LUMO? HOMO. Okay, so I got 2 votes for LUMO, 4 votes for HOMO. It's going to be where the electrons are, right? So if the electrons have to move, then it's going to have to be where those electrons are. So it is going to be the HOMO. So it's going to be the highest occupied molecular orbitals. You need those electrons to move. So it's going to be where those electrons are effectively at their highest energy. Okay, does that make sense? Okay, so it is going to be the HOMO, and so this is the one that we're going to sort of want to consider. Now, in the same way with the Diels-Alder, right? We're going to go ahead and draw this process here. So with the HOMO, what we're going to have is these 2 groups sort of opposite one another. So again, like in the Diels-Alder, you want the nodes to sort of go together, right? And so this is why if we have groups out here, what's going to happen is these nodes are going to want to come together. And so the way that they're going to do that is they're going to come together in this way, right? So what's going to happen is as this sort of rotates as these processes take place, at least with the stereochemistry that I have drawn here, right? R group over here, right? Again, we have a hydrogen in the middle. That R group is going to come up. right? And again, over here we have the hydrogen, but as that flips forward again, that R group is going to come up. Okay? Okay? So in a thermal process, the stereochemistry that we're going to get is going to be contingent upon this sort of what we call disrotatory process. So this is what we would call disrotatory. Okay. Again, I think the sort of nomenclature here that you sort of use, you got to sort of figure out a way to remember what disrotatory is versus conrotatory. If you think sort of con is sort of like away from one another, so you can sort of think of the rotation this way. If you want to sort of think of disrotatory, I don't know, anybody?
I just think like con is with instead. With, right? It does. So
that's good.
With each other is cool.
Yeah. When I was in grad school, I had to come up with something kind of. This is kind of bad. I almost want to pause this, but sometimes, because sometimes you just remember things based upon like ridiculous stuff, right? And so when I was, so I'll just go ahead and say it, whatever, and if it shows its way out there. So do you guys remember? So when I was in college, this one summer, it was actually the summer after I took organic chemistry. So it might have been the summer before I started taking more advanced courses. One of my roommates was like big into WWF, right? And so he would like watch WWF. I guess now it's WWE, but like the wrestling, the fake wrestling, not the worldwide like federation, but like the fake wrestling, right? And you know, they have all these characters that are all very angry at the world, and there was this one guy, there was this group of people. Anybody here watch WWF? Used to. So there was this group, so maybe this will help you guys remember it, and the rest of you perhaps. But there was this guy called Triple H, right? I think it was like him and all of his group, and they would always go like this or something like that, right? So they always go like this, right? So they go like this, right? And kind of what they would be saying is kind of like suck this, right? And so that's how I always sort of remembered disrotatory as like from these guys from like WWE. So again, completely inappropriate, but sometimes those inappropriate things help you remember stuff. So so that's how I always sort of thought of it, was disrotatory. So if that helps some of you guys, I think he's going to remember. What's that?
That's actually more inappropriate than I thought it was going to be.
What, suck this? So, yeah, no, it is a little inappropriate. So, anyways, but it helped me remember, and it's how I remember, and so at least it's appropriate in the way in which maybe it's a remembering tool for you guys. But, so anyways, that's the way that I remembered it, if you can remember conrotatory or whatever. But that's how I sort of remember the distinction between the two. But certainly this is sort of a disrotatory process. I still remember it 10 years later. But again, so this is when you're thermal, right? So the idea here is this is when you're thermal. Okay? But if you are now in a 6-pi electrocyclic process and you are doing photolytically and you're trying to get this to be promoted photochemically, then what's going to happen? You're going to excite the electron, right? So what's going to happen is now suddenly this is going to be the HOMO, right? And so in a thermochemical process, now this becomes the HOMO. So photochemical process, we're going to excite this. Now this is going to become the HOMO. And so in this process, what would happen, right, is that you're going to switch one of these. And now what's going to happen is it's going to be conrotatory in nature, okay? And so now we're sort of going this way, right, as Nicole's sort of saying, is sort of with one another, right? And what's going to happen here is as this proton's there, as that swings up this way, now the proton's going to be up and the R group is going to be down. Okay, so at least from a 6-pi electrocyclic process, because these are some of the most common ones that we use, are going to be the 6-pi electrocyclic ring closures. This is going to be sort of your disrotatory. It's going to be thermal. And in terms of photochemical, again, don't memorize the stereochemistry because that's going to be dependent upon what your stereochemistry starts with, right? So depending upon what if this was the other way, then you would get the other one. The point is that this rotatory versus conrotatory, okay? But again, you don't want to memorize this. I think it's just best to sort of think about it at the molecular orbital level, because if you try to memorize all these different things, it's going to be too much and so forth. So again, if you go to now, say, 4-pi electrocyclic ring closure, right, then all you would do is you would just think about where the HOMO is for that for a thermal process, right? And you would just sort of think about where the nodes are and sort of have them lined up, right? And so in that case, thermally in a 4-pi, it would probably be the opposite. It would be sort of the same as the photochemical is, so it would be sort of conrotatory in terms of the product that you would get, okay? So this is sort of the way to think about the stereochemistry of electrocyclic processes, and doing so through a sort of molecular orbital standpoint. Yeah, no.
I have a question here. The photochemical, you excited to the next energy level, right?
Mm-hmm.
If you excited to size 5, it becomes thermal. Right?
Yes. So you're just wondering. I'm not that familiar with that stuff. So I see what you're saying. Could you jump? Could you jump?
Jump one. Then
Yeah, the person.
that becomes thermal, but then it's photochemical.
Yeah, but then you'd have to sort of do a double jump. I'm not sure. The person you'd have to talk to about the potential of even doing something like that would be like Alec Greer or something like that. I'm not as familiar with that type of. I don't even know if that's possible. It might be possible. There might be a way that you could do it. I just don't know.
It's just an energy gap, right? And it's the difference between the frequencies.
Yeah, I don't know. I don't know. But I've never seen it. I don't think if it is, it's not the sort of classical way to think about it. So if there are, it would certainly be something much more complex, and you'd probably want to ask, like, again, Alec Greer would be a good person to ask about that. There might know. Because I see what your sort of thinking is, and I think that in terms of tuning that, there may be ways that you might be able to do something like that, but I can't even begin to fathom. So, okay.
In the next, you have like a switch and spin before you have another jump.
You guys are going beyond me right now in terms of what I'm even close to remotely prepared to talk about. So again, I think that there may be, if you sort of took a photochemistry class, there may be ways to sort of do some. You might actually. Yeah, I think Greer. Yeah. So anyway, so Greer would be at least the person that comes to my mind if you had these questions if you're ever on campus, stop by his office and ask him that. I'm sure he would be very happy to talk to you about the sort of nuances behind this stuff. So anyway, but at least in terms of a classical understanding of sort of thermal electrocyclic ring processes and photochemical electrocyclic ring processes, this will help us sort of explain this. Okay, and so for the remainder of the course, what we'll try to do is use this to figure out what is going on over here. Okay, and then we'll sort of, if we have time, we'll show how Nikolai went ahead and made this, but that's kind of not really all that interesting compared to, I think, this specific stuff. So if we have time, I'll talk about how he made it, but I think more importantly, I want to sort of discuss the chemistry and how these were made in a way that's going to reinforce our sort of understanding of molecular orbital theory in the context of stereochemistry of electrocyclic processes. Okay, so let's start with sort of just endiandric acid and sort of process is going to take place sort of right from the start. And so what we have here is, instead of a 6-pi electrocyclic ring process, now we have an 8-pi electrocyclic process, okay? And so the first thing that we're going to do with this mechanism is we're going to close up this ring. And so the question that I have for you guys is, what's going to be the stereochemical outcome of the 8-pi electrocyclic ring closure? So we discussed 6-pi, which is the most common, but in endiandric acid, it's going to be an 8-pi electrocyclic ring closing process, okay? I want you guys to all, don't let anybody say anything. I want everybody to sort of, you have to draw it out. The question is, everybody just sort of draw it out and think about the stereochemistry. You have to use a piece of paper and pencil. So everybody sort of think about this. What is the stereochemical outcome there? Is it going to be cis? Is it going to be trans? And I would suggest, even if you have an idea and you've got some shortcut that maybe you did in your mind based upon what we did with 6pi, maybe just draw out what the HOMO is and sort of think about whether that would proceed through disrotatory or conrotatory and what the result of that would then be on the stereochemistry. Again, the first question is, what are the nodes on the ends? Second question is, will that lead to conrotatory or disrotatory? And then third question is, then what is the result of that on the stereochemical outcome? Because sometimes it's easy to see, sometimes it's easy to be like, oh yeah, it's con, or sometimes, oh, it's disrotatory. But then actually then translating that to the physical stereochemical outcome can be a little bit challenging. So it's one of those things that I think is worth it to think about. So let's just start with let's start by thinking about where the HOMO is, right? Because this is going to be thermochemical. So we want to figure out what the HOMO is, okay? Without having to draw all 8 of these, let's just think about the sort of nodes on the end, right? We're going to have 8. Which means it's going to be the 4th highest in energy, which is going to be the HOMO. And again, if we just think about what's on the end here, right? We've got, we'll just go up to the HOMO. Get them away from one another. So at the lowest level, how many nodes? 0, so they're going to be on the same side, right? Next one is going to be 1 node, so it's going to be opposite. Next node is going to be 2 nodes, so they're going to be on the same side. And then the third node, which is eventually going to be the HOMO, is going to be, same side, and then back to opposite. Okay? So the HOMO in this case, again, because it's the outside ones that we care about the most, right? We don't really care about what it is on the inside. Those can actually vary depending upon where you physically draw those nodes. So what we really care about is the carbons where the bonds are going to be forming. Okay? And so in this case, now what we have to sort of realize is that we have at this carbon, what we have is sort of opposite, right? And so sort of second part is, if they're opposite, is it disrotatory? Are they going this way? Or are they going conrotatory? Right. So in this case, again, they're going to go conrotatory, right? So they're going to sort of go towards the same direction. And then I think the thing that takes a little bit of time to really, and I would urge you guys to really sort of try to think about this and really get your brain around is what is the result of that then going to be on the stereochemistry? Is that going to lead to these being, these are going sort of opposite, right? And you have this stereochemistry as shown. What's then going to be the net result of the stereochemistry? Does anybody? Right, they'll be opposite side. Okay? And so as sort of drawn here, specifically as I've sort of rotated this, right, the proton is going to go down, and this group is going to come up, right? So if you think about that, right, so we're rotating this way into the board, right? So the proton's going in. And on this other side, right, what's going to happen is at this point now, we're rotating that same direction, but now the proton's going to come up. Right? So if you think about that proton at that position, now the proton's going to come up and that group's going to go back. Okay, so it's going to be trans. Okay, it's going to be opposite stereochemistry. Okay, so that's the first thing that's going to happen. But now we're set up for something else, right? Yeah, we can have the other enantiomer as well, so it can go either way. But now we're still under thermal conditions. What are you saying?
You have another ring.
You've got another potential ring to form.
Yeah. Double bond and stuff.
Right? Okay, so let's think about this one. So I want everybody try to draw the product behind it. So now we're at a 6-pi electrocyclic ring closure. We're still under thermal conditions. Okay, so why doesn't everybody try to draw that 6-pi electrocyclic ring closure? And let's think about what the stereochemistry of that would be. Okay, so at this point, we're actually going to have diastereomeric mixture because we can go in one of two ways. But we'll just draw the ones. Well, we can draw both of them. So these would be, we would get both enantiomers here. So we would get one up, one down, one up, one down. When we do this, when the process takes place, whether it's disrotatory or conrotatory, it's going to lead to one's going to go one way, one's going to go one way or the other. But in terms of the diasteric chemical control, we can actually get two mixture diastereomers here. So how does everybody try to draw that product? Take out a piece of paper and try to draw this 6-pi electrocyclic ring closing process. And what I'd like you to do is draw both. There's going to be two diastereomers, so try to draw both diastereomers. All right, so we got anybody?
Is there a few? Well, I didn't look at paper. This is like coming, like flat. Yeah, I could, put that this is the other person. This is I'm trying to show.
Was it time?
What's con? Yeah.
Let's go.
Oh, this?
Yeah, it's
Is
this.
this? Damn it.
Yeah, so
Wait,
let's no, it's fine. So let's go through it together. So at the surface, let's ignore the stereochemistry and let's just think about the bond connections, and we can worry about the stereochemistry next. Okay, so we're making a 6-membered ring. It's going to be here, and then that 6-membered ring is then going to be combined with a 4-membered ring. So right, so we're going to have this sort of 6-4 ring system.
Sorry, I said con.
Okay, so okay, so this is a sort of general structure, and what we're concerned about is the stereochemistry, right? So everybody hopefully sees how this 6-pi electrocyclic ring closure leads to this sort of 6-4 ring system, right? Or this 4-0, 4-2-0 octabicyclo, octane, or whatever it is. So the point is that this is the compound, and the question is, what's the stereochemistry there? So let me just ask you guys, just even before we think about, and we'll go through the sort of the orbital with this, but even just thinking about, could that even be trans?
It'd be like really ugly and twisted.
Yeah, I mean, I don't want to say it couldn't be, but that would be really strained system. So the likelihood is that when we're looking at this, you can sort of look at the ring system and assume that it's going to be a cis ring system. So it's probably going to be coming towards you and going away from you. But let's actually look at that, and let's think about the 6-pi electrocyclic ring closure process again. So again, fortunately here we've got everything sort of figured out for us. So let's just erase this one, erase those two. And now we know that our HOMO is going to be on the same side, right? So this is for our 6-pi electrocyclic ring process. So this is going to be the HOMO in this case. So the nodes are going to be on the same side of one another. And so what we're going to do is when we draw these nodes here and here, they're going to be on the same side, right? And so what's this process? This, right? So it's going to be this rotatory. So as I've sort of shown here, what's the stereochemistry going to be as I've sort of shown? As I've drawn, as these are coming towards you, what's the fate of the protons? They're coming towards you as well, right? So they're going to be coming out or up. Right? So they're going to be coming that way, and the protons are going to be coming up. Now, there's nothing to stop us from going the other way as well, right? Because there's no necessarily symmetry, but if we sort of just draw the other one, and we go this rotatory the other way, okay, so if we're going to go the other way, right, so now if we're going, oh my god, I can't even bend my arms that way, but now if we're going this way, right, now our sort of protons are going to go back, right? So in this case, protons will go back. Okay, so what we've generated now at this point is we've got effectively 6-4 ring systems, right? So here we've got 6-4, here we've got 6-4, and the question sort of becomes then how, from these processes, do we now start to get to these other processes? Yeah.
Just a quick structure question about that. The 2 hydrogens you have on the right-hand side, that's not a 4 and a 3. That's just a 4 member with the 2 hydrogens being shown.
Oh, yeah. Yeah.
That's another question about the product. Is that 4-member cycle going to be
So 4-member rings,
normally bent, right?
yeah, I mean, again, it's going to depend upon, usually we'll maybe bend a little bit just so that not everything is eclipsing.
Yeah.
But by the same extent, to sort of bend out, sometimes then you're creating greater strain. So I'm not that familiar with what the lowest energy is.
You have two pretty big groups, and they're trans to each other, so I would imagine that those, if you were to draw the stereochemistry of the other two corners, that they would be opposite.
Yeah, I mean, it's possible, again, you know, four-member, so cyclobutane rings are always going to have a high degree of torsional strain, right, based upon the fact that you're effectively often locking them into these sort of eclipse conformations. Not exactly eclipse, because then based upon the ring strain, you sort of bow them away from one another a little bit. But yeah, I'm not entirely sure what effect that necessarily has on what the lowest energy of that specific conformation is going to be. So I don't know. I mean, I usually think of cyclobutanes as planar, just because once you start to bend one ring, and you're creating a lot of ring strain somewhere else. But it's probably going to depend upon the substituents and the degree of torsional strain and what the energetic benefits are to sort of bending slightly out of plane versus so it's going to probably be very specific.
Well, the reason I think you asked this question in the cycle or in the organic spec class a bit ago. Remember the four-member ring? And it turns out that the hydrogens are not chemically equivalent because of them.
Oh, are you talking about like? Oh, I think what you're referring to is the high degree of S character. Like, for example, like in cyclopentanes, for example, we often think about like banana bonds, like bent bonds. Is that what you're thinking
No,
about?
I was just thinking about how four-member rings are normally not.
Well, it might not be the what it sounds like. Again, I don't know. We have to look through your stuff. Maybe we can discuss this afterwards. But in general, when we think about strained ring systems, I don't know too much about this in terms of cyclobutanes, I've got to admit, but at least in terms of cyclopentanes, cyclopropanes, is that oftentimes when we sort of think about these, we think about the bonds not being linear and bent, so we often think about them as being sort of bent bonds, sort of like this. And so a certain amount of the sort of ring strain is sort of mitigated by this ability of the bonds to physically sort of bend and adopt these sort of banana bonds.
That's not what I'm talking
That's
about.
not.
Because you can't, there's no possible way you can bend a three-member ring. Because it's 3 points. It's always pointing.
Yeah. So again, I'm not entirely sure. So in terms of how a cyclo, whether this would bend up a little bit or bend down a bit. So certainly.
Two diagonal corners.
Like a book.
Yeah. Yeah.
Yeah.
Right.
To sort and again, the whole reason behind that would be to relieve the torsional strain between like these two eclipsing, right? So I guess that makes sense. In this case, it might be more difficult to do this. Is that what you're thinking? Is it sort of constrained within the ring?
I can see how it can be bent there.
So with the let's when we draw. So I'm going to draw these in 3 dimensions. So maybe once we draw it in more 3-dimensional orientation, it might be that way. But I'm going to not probably draw them. I'll probably just draw them planar. But anyway, so sort of at this stage, really what we need to do at this point is in each of these cases an additional manipulation is going to take place, okay? And so it turns out that in both of these cases, what's going to happen is the final step towards these two are going to be contingent upon Diels-Alder chemistry. So the last step in both of these, even though the first 2 steps are the same and the last step is the same, different Diels-Alder reactions are going to end up leading to different potential products. And so in the case of yeah, and that's the same like in terms of the It's the same thing happens. I'm more familiar with what you're talking about with cyclopentanes as well. Because cyclopentanes, that's why they adopt envelope conformation.
Yeah.
The same way, it's kind of like the same reason that share is kind of a
Share and
share
vote,
configuration. Yeah. Okay, so anyway, so in this case, if we sort of think about this, when we look back at these, right, what we have here, again, we have our six. We have this sort of 6-4 ring system, and what's going to happen is a Diels-Alder is going to take place, right, between this diene, right, and one of the alkenes again. So if you think about this 6-4 ring system being one of these 6-4 ring systems, what you have is you can have an alkene on one side react with a diene on the other in a Diels-Alder sense. Okay? In the other case, here's our 6-4 ring system, but in this case, what we're going to do it's going to be a Diels-Alder reaction between the diene of one of these and the sort of alkene of the other, okay? And the ability of one to do one and the other one to do the other is simply a matter of the two diastereomers that we've shown here. So in the one case, again, the sort of protons, so in the one case now, if we look at these, what we notice is that, sort of breaking it down, the real only difference between these two molecules, despite how different these ultimate structures look like, is simply the relationship between what would be appendages and the protons, right? So in this case, if you sort of just block out that cyclobutane ring there, the sort of carboxylic acid-based one is actually opposite the protons, right? And in this case, it's the sort of diene part that's opposite. So if you sort of look at that diene there, that's on the same side of the protons over here. It's on the same side of them there. So when we actually physically draw these out, you might be able to see this a little bit better. Okay? And so what we'll try to do is we'll try to draw it perhaps a little bit more three-dimensional. Okay, so in this case, the molecule that we have here, okay, so what I've got here is a 6-4 ring system, okay? Now, I just drew the okay, so this is, okay, so again, the protons are coming up. I've sort of just bent it down this way. Okay, so in this case, what we have is coming up on the same side of the protons is going to be this part here. And what's going to be coming down on this part is going to be that other part. And so, again, now you can start to see how, got a proton up to help us there. You can now start to see how you can get that Diels-Alder reaction there, right? And so what that's going to lead to is once you physically do that Diels-Alder reaction, what you're going to get to is right, it's going to be the Endiandric acid C. Sorry, Endiandric acid C, yes, there you go. Endiandric acid C. And again, if we redraw this one the same way, so now in this case, oops. In this case, we're going to flip-flop it, and so now the protons are going to be coming up. sorry, protons have to go back. Not easy to draw. Okay. Now in this case, now the protons are going back, so the one that's going down is this one. And what's going to happen over here is that now we're going to have right. So now we're going to have that diene coming up, and now what can happen is that diene can now do the Diels-Alder over here. It's going to be the diene from that one part with the other part, and then this is going to ultimately lead to nitric acid. Nitric acid. Okay? Okay, so this is the sort of general idea behind this. Again, it sort of reinforces the sort of electrocyclic ring closing processing, getting us to think about the way in which you can sort of do these. So in reality, what I've sort of just done right now is I haven't even really discussed any of the synthesis per se. I've just sort of discussed the background behind the way that these molecules might be made. So what I'll do with the remaining time is I'll just sort of tell you a little bit about what Nicolau did, and then I'll show you one example of how he went about synthesizing the sort of polyenes and how he went about getting them. So in general, the endiandric acid process, or at least Nicolau's work on synthesizing the endiandric acids, because again, there's many different versions of these that are just based upon different stereochemistry and stuff. They generally fall in this kind of similar ring structures to the ones we've shown here, although some of them are a little bit different. But in general, what he did was he sort of used this, in reality, the sort of strategy that he leveraged was really just these two first steps. So you know, whether or not he had a diene here, for example, so in some cases he would have the sort of core, you build up the core here of the sort of of the sort of trans. You basically set up the molecule for the 8-pi electrocyclic ring closure followed by 6-pi electrocyclic ring closure, but then what he might do is instead of having the diene here, he might have some other group that he could later functionalize. Or something over here that he might be able to later functionalize. And so this is sort of what Nicolau did by and large, was sort of, let's leverage this 8-pi electrocyclic ring closure followed by a 6-pi electrocyclic ring closure, and let's use that approach as a really quick way to get entry into this entire class of natural products, and thereby sort of highlighting the method and showcasing how the method could be used to strategically make these molecules quickly. And on the sort of flip side, helping kind of confirm that these might actually come from these, from all the same processes, sort of confirming the hypothesis that that's how these were made. Now what I'm going to tell you about is just sort of, I'm going to give you guys an idea of how he made these, and instead of going through and synthesizing all the different classes, I'm going to show you how he synthesized this structure. And because by and large what he did was he sort of made this structure, and I just shown 2 of the molecules that he made, but he would make slightly different versions of these, and he would just heat it, and you would get like 4 of the different endiandric acids, right? So you would isolate each of them and you get a slightly different yield. But so I'll just to give you guys an idea of how he actually made these molecules. I'll show you how he made this specific one here, and then that would pretty much be the end of it there. Okay. So again, this is all the cool stuff, but it's worth it just to talk a little bit about chemistry from the standpoint of synthetic chemistry.
Okay. Is there a reason that he was making these, or what were the androgens?
Yeah, I mean, so again, they represented, I think, I don't know, I don't know exactly if there was any biological importance behind them or whatever. I think it was more. Again, I think this was like in the 77 or something like that, like in the late 70s. So I think that this sort of reason behind this work was more to, I think, help illustrate some of the Woodward-Hoffman rules and stuff like that, and sort of more highlight this as a general approach. Again, what you have to remember is that a lot of the work that was done specifically in the 70s, 80s, and it stopped happening in the 90s. There was funding to sort of, and there still is today, right? Yeah, sort of synthesis. I don't want to say necessarily synthesis for synthesis' sake. Certainly, when you say synthesis for synthesis' sake, I think it's more kind of like a synthesis as a training tool to help make people really good synthetic chemists, which is, I think, one of the main and perhaps one of the strongest benefits behind doing total synthesis. But it's also just used to help us validate some of our understanding of chemistry. So I think the sort of knowledge that's gained through the synthesis is also important. So I think it was probably more a pursuit of really understanding this Endiandric cascade, trying to gain credence to it and sort of show how it could be used to rapidly generate otherwise complex targets. So I would say it was more for, it wasn't like he was trying to make them, I don't think, to generate Endiandric acid C, which is anti-cancer or something like that. I mean, again, I'm not entirely clear, maybe they did have that activity, but my guess would be is it more to sort of understand this cascade and actually showcase it.
I just looked it up and it just said it's like an antibiotic.
So yeah.
They have like a biosynthetic route.
Yeah. So right. So there might be a way that you could, again, that's like what we talked about when Rick was here in terms of a lot of times some of the antibiotics that we have specifically actually just come from like a yeast or something, right? Like they get the yeast to harvest it for them. So yeah, I don't know that his drive was to, I mean, maybe he might have spun it that way, but I would bet that his real drive was to gain a better understanding of the chemistry and to show that he could actually do it. Because it is freaking sexy, right? It's a really...
I was just thinking that, with all the molecules that you don't have like a biosynthesis for, it might have like antigens or something, or it might have a function to it.
Right.
You wouldn't be able to get synthetic routes to that if you didn't have this precursor, this work done on stuff that maybe there are.
Yeah, I mean, it's possible. Again, it's all knowledge, right? It's sort of like, there's the reason why we do different things of research. They come in various forms, right? That's kind of why we have the NSF, right? The NSF sort of goal is to sort of maintain a knowledge base, and they try not to worry too much about the sort of practical application of it. It's just knowledge is important. We continue to generate knowledge, and at some point the hope is that knowledge will lead to something that's the betterment of society. But by the same extent, a lot of times it's just because we want knowledge. You know what I mean? We're trying to feed our own desire to have that kind of stuff. But even in some of the like most out there things where you're kind of like, well, what is the purpose of that? You can still look way down the line and imagine that there may someday be a benefit of that. I mean, think about a lot of the stuff that like NASA does in terms of like trying to identify new stars and different planets and stuff like that. It's like, what's the benefit of that on current society? Well, currently nothing, but eventually our world is going to be consumed by the sun, And so in terms of the long-term survival of, I'm talking, don't look at me like it's going to happen next week. What I mean is like,
it's like where this is going. So.
No, my point is that for if as a species we're going to survive, we can imagine getting away from plagues, we can imagine our own destructive natures of killing ourselves, but as a species someday we may need to, Earth will no longer be, I mean that's inevitable, like this planet will no longer be there someday, many billions of years from now. So even some of these things that NASA is doing, which at the surface currently might seem like don't really have a practical application, like they identify a hospitable planet for us to live on. I'm just using a sort of a very dramatic example of science that might not seem to have practical applications now, aside from the sort of creative and intellectual interest of society. The problem is there's a lot of people in Washington that don't really care about this sort of intellectual side. So oftentimes there does need to be a practical side. What's that? Right. So anyway, so the point is that this becomes his target that he needs to synthesize, and this is where we'll have to go to this guy here. And so in terms of how he's going to do this, it's difficult to sort of synthesize this molecule because it turns out that this cascade can oftentimes just be set off. Like you don't even need to heat this to happen. It just sort of happens spontaneously once you get this 8-pi electrocyclic process together. And so sort of thinking backwards, what he does is he wants a trigger, right? So he wants some type of a method to be a trigger. And so what he's going to do is he's going to anyways, where I was going was I was saying that sometimes knowledge, it might not have something that seems immediate, but at some point that knowledge will potentially have big value. So anyway, so this was going to be his sort of precursor. So we figured if you can get to this precursor, then you could get from here to here. How would you guys do that? Yeah, how do you take an alkyne? I mean, there's a few different ways, but what's the sort of practical undergraduate? Lindlar's catalyst, right? Exactly. So you'll probably do Lindlar's and H2. Right, so you can take an alkyne, you can turn it into cis alkenes, right? So, and that's what he's effectively going to do, and then he sets off. Like that's how he sort of generates his molecules, and that set off all the other stuff. Again, anytime you're doing retrosynthetic analysis, it's often best way to sort of break it into 2 equal-sized pieces, and that's kind of what he does here as well. This becomes his bond disconnection, sort of this alkyne, right? And so you can imagine there's a lot of ways that you can make acetylene.
One of the main reactions that you want?
What, the Lindlar's reaction?
No, the other one that we are going to use.
Oh, yeah. So alkyne coupling reactions. Again, there's ways that we can do this, and so the fragments that we'll have at this point will be okay. So this guy and a little bit more forward space for this one. Okay, so anyway, so these are going to be our 2 sort of intermediates at this point. These are actually each going to come from, effectively in both cases, these are actually both going to come from alkylation chemistry. So what's going to happen is he's going to use, so this is going to be a very similar strategy for both of them. To sort of make these carbon-carbon bonds throughout here, what he's going to do is he's going to leverage reduction conditions. So this sort of sulfur is going to serve as his sort of what do you call it? Did I draw this right? Oh, I'm missing an alkene here. Why don't you guys tell me that? Come on, guys. Yeah, I'm missing an alkene there, but everything's all screwy. So that's why I was confused. So this is not this. Okay. Yeah, but this is like boring. I think. I mean, honestly, like I can keep going through the synthesis, but it's not the cool stuff behind the synthesis. So again, if you want to read behind the way that he made up these molecules, I think it's sort of anticlimactic at this point. I think the point behind the synthesis is he's able to sort of build up, come up with a way to make this. I'm sure all you guys could probably come up with a way to make this molecule. You don't need somebody with Nicolaus' brain to be able to synthesize this molecule. But the fact of the matter is, he was able to do it. I think, one thing just to point out is that when he was like dissecting this, you sort of think about breaking it from the middle. The point is that he was able to make this, and he sort of was able to sort of play around with all these different cascade processes and make these different molecules. But again, I think the take-home lesson behind all this is, again, the sort of idea of diastereoselectivity of electrocyclic ring closures. This is something you guys should all familiarize yourselves with and sort of get comfortable with, and thinking about sort of Woodward-Hoffman rules within that context, and sort of recognizing that they can be powerful ways to make carbon-carbon bonds with specific stereoselectivity, specifically if you're trying to make, say, for example, a medium-sized ring or something of this nature. So, okay, so with that, do we have class next week?
Yes.
It's the following week that we have off. I know that there's like a week that we have off at some point, but so anyway, so next week, I'm trying to think of what we have in store for next.